All right, stats. So time to go over the questions from 10.1. So there are only 3 questions to go over. I'm going to go over the first one in a lot of detail, and I'll probably just mainly show you the answers for the other 2. I hope that this week you kind of saw that, hey, this isn't too bad. I think I'll be able to do this on my own. So the good news is chi-squared tests, even though the wording of them can be a little tricky, the process of solving them is actually not terribly complicated. So question number 1 says that the person R. Wolf rolled a die 20,000 times. The results were recorded in the display below. Is this evidence that the die was unfair, or is it approximately what you would expect from a fair die? So this is kind of a not so subtle way of them trying to get you to say, hey, maybe I should run a chi-square goodness of fit test. So it's a die, so realistically, as long as he chose his die at random, I mean, that's about the only randomness that we really have here is, did he choose a nice random die before he got started? We'll assume that he did all of his rolls properly. For example, if I'm rolling a die and I'm rolling it on a hard surface, I would want to make sure that if the die rolled off my surface and onto the floor, I probably don't count that result because you have odd things like that that can occur. But nonetheless, we'll assume that all the die rolls were proper. Okay, now, does everything fall into one category? We would certainly hope so, that you shouldn't be landing between sides. All right, all the expected values are going to be very, very large because we expect all of them to occur, whatever 1/6 of 20,000 is. We certainly know that's more than 5. So everything falls into one category. We have our model, which is that they should all occur equally likely, so 1/6 of the time each. We definitely have at least 5 in our expected values, and we hope the die was chosen at random. So my null hypothesis on this should be that the die is fair, meaning that each outcome occurs 1/6 of the time. My alternative hypothesis would be that the die is unfair, which is at least one of the sides is not occurring 1/6 of the time. So let's take a look at my calculator. You guys are going to see that I have it typed in maybe what you would say is kind of weird. I put in the observed values in list 1, but then in list 2, I only typed in the number 1. And I mainly did that to show you guys how you can speed up this process. So I did that because now what I'm going to do is I'm going to highlight list 2, and I'm going to tell the calculator to take all the values in list 2, and I needed there to be 6 values. So I'm going to have it take list 2, divide those by 6, which will be 1/6, and then I'm going to have it multiply those values by the number of times that they rolled the die, which was 20,000. Enter. Now you will notice that my expected values include a decimal. You might be asking yourself, is that okay? And it is. Even though you can't actually have a die occur on 1/3 of a roll, you can have expected values that are in fact decimals. There's nothing wrong with that. Okay? So this is what it should look like. Now, let's run our test. Stat, test. Way down towards the bottom is the chi-squared GOF, goodness of fit. It's option D, as in dog. The observed values are in list 1. The expected values are in list 2. Since a die has 6 outcomes, the degrees of freedom will be 6 minus 1, or 5. So then I calculate. I get a very large test statistic and an extremely small p-value, which is pretty interesting because that means that there's extremely clear evidence to support that this is an unfair die. That means the result was so statistically significant, I am rejecting the null hypothesis, and there is something wrong with this die. So there you go. So if we look at the book's answer, it goes through the conditions. It tells us that all the stuff is what it is. They listed this in a table horizontally, which just drives me insane, but you can see the numbers are plugged in. We'll come over here to list 2. It said the null hypothesis, the die is fair. The probability of each is 1/6. The alternative, the die is not fair. I would have preferred them at least put in that at least one of the sides does not occur 1/6 of the time. You can see the very large test statistic and the extremely small p-value, telling us that our conclusion would be that there is something wrong with this die. It does appear to be unfair. Okay? And that's really all there is to this, guys, so there's not a whole lot. If I look at the other questions that are being asked, the next one I had you do was number 5. And it says Gregor Mendel performed an experiment to try to validate the predictions of his genetic theory. He experimented on different types of peas and thought he would end up with a distribution of 9 to 3 to 3 to 1 based on smooth yellow, smooth green, and wrinkled green. His experiment resulted in outcomes of 315, 101, 108, and 32. Now, I will say that in the past, the only place I see sometimes students go wrong is on their expected values. I get a few people who are confused as to what they're supposed to do. So what you would want to do is you would want to come down here and figure out exactly how many there are here. So there is 9, 3, 3, and 1. So that means the ratio is out of 16, because if you add those 4 numbers together, you get 16. So basically, the first group is 9 out of 16. The second group is 3 out of 16, 3 out of 16, and 1 out of 16. Now, the next thing you'd have to do is count up how many peas there are. 315 plus 101 plus 108 plus 32. Now, I'm going to try to do that real quick to the side. You guys aren't going to see me adding those together, but me adding those together to speed up this process, if I was actually on the right screen on my calculator, is giving me a result of 556. So there's apparently 556 total peas. I apologize. So you can see the observed values for list 1. You would just type in 315, 101, 108, 32. And then for the expected values, you would need to do 9 out of 16, 3 out of 16, 3 out of 16, 1 out of 16 times 556. Just to show you guys how you could speed up that process for list 2, let me give you a quick little, here's how I would do it. So let's pretend list 2 is clear. And then I would do 9, enter, 3, enter, 3, enter, 1, enter. And very similar to the last question, I would tell the calculator, take everything in list 2, divide by 16, multiply by 556 peas, and get my answers. I'm sorry again. So that to me is the fastest way of getting those answers. So if you look at the observed values and then you look at the expected values, not only are they close, but they're like horrifyingly close. This seems like a very random thing for somebody to just like accidentally predict, right? So let's see what his result is. So you can read the null hypothesis. Peas are produced in the following distribution: 9/16 smooth yellow, 3/16 wrinkled yellow, 3/16 smooth green, 1/16 wrinkled green. And the alternative, I like how the book just simply wrote, peas are produced in some other ratio. I think it would be better to state that at least one of the types of peas does not fit the model distribution. It's almost like the book got sick of being proper. So if we come down here, we get a test statistic of 0.47. And where is my p-value? I don't see the p-value listed, interestingly enough. Well, anyway, their question was, did we think that this was suspiciously close? And it says the p-value in and of itself is a bit suspicious but not conclusive. However, Mendel performed several such experiments, and in each case the p-value was suspiciously low, leading statisticians to believe that the data may have been fudged. So basically what you should have noted, oh, there was the p-value. I don't know how I overlooked it. 0.0746. So his result was so consistent with kind of what you would expect that it was one of those things where, well, maybe he made this up, because it does seem like something that would be very odd for somebody to just kind of guess on their own. So it is one of those things where, yeah, pretty interesting, right? So let me just type in the numbers so you guys can see those numbers plugged in. We had the 315, the, 315, 01, oh my gosh. It's just like being back in class where Mr. Ryan can't type in anything correctly, right? 8. And was it 32? Yeah, 32. Answer will delete. Oh my gosh. Yep, it's definitely just like being back in class, guys. I still can't get the things to want to be nice to me. Okay, so if I run this goodness of fit test, I wasn't intending on doing this one, but now I've made it to the point where I've decided to do it. So since there were only 4 types of p's, we'll do 3 degrees of freedom, and we will calculate. So now you might be wondering why our p-value is very large and their p-value is very small. They're basing it on the fact that getting a very large p-value is on the other end of the spectrum of rarity, right? So that means that we are getting something that is so likely, it would occur so likely that we're more likely to have had the opposite result happen. So they took the difference between the 0.925 and 100%. So basically, if you get really, really big numbers, then that means your results are almost too accurate. And so that's why they are talking about him possibly fudging his numbers. So it is one of those things where the p-value is actually very large, resulting in something that should have only been this large about 7.5% of the time. So kind of interesting. Yeah, it definitely looks like he was probably manipulating his numbers. Okay. All right, and the last one was fun, right? I'm sure you had a ton of fun with this one. So all you had to do was take the actual results, which were the 50, the 45, the 3, and the 2, which is what actually happened in the election, plug those into list 1, and then compare those to each of what they thought were going to be the expected ones. So you could have done these one at a time, done Crossley in L2, got your answer. Done Gallup in L2, got your answer. Done Roper in L2 and got your answer. Or you could have typed each one in a different list and kept changing your expected value if you wanted to. Really totally up to you. Now, you probably noticed that technically speaking, our expected values did fail in all of these things because they weren't all at least 5. But realistically, I never really cared about the prediction of Thurmond and Wallace because our goal was to kind of just see if the Truman and Dewey thing was the thing that played out. Because that was what was important in the election. So no, my results might not be so accurate for the other 2 candidates, but realistically we didn't care about those candidates anyway because they didn't have a chance to win. So if you were curious about that, yes, that condition did technically fail, but we're not terribly concerned. All right, so let's just look at the answer for number 7. So you can see each poll resulted in its own thing. The Crossley poll ended up with a really bad p-value, 3 times 10 to the negative 12th. The Gallup poll ended up with a really, really small p-value, 3 times 10 to the negative 23rd. And then the Roper poll, holy moly, 2 times 10 to the negative 49th. That means that every one of these polls failed, okay? So all of these polls failed drastically. If you were going to rank them, technically, the Crossley poll was the most accurate because it has the largest p-value, and the Roper poll was the least accurate because it has the smallest p-value. But nonetheless, all 3 of these polls were terrible. None of them did a very good job of actually predicting what the actual result was. So that's what you were supposed to know, okay? So hopefully, guys, you kind of picked up on what's happening. Expect there to only be 1, maybe 2 questions on the quiz this week. They're going to be related to goodness of fit tests. If it's anything like the last 2 weeks have been, your guys' quizzes have been pretty decent. Your wording is pretty good. You guys are following directions. I'm real happy with the work so far. So just keep on rolling. Get those quizzes submitted to me before Sunday, and I'll see you guys or talk to you guys next week.